And if you have questions about the homeworks, you're welcome to stay behind and we can talk about it. Okay. Now, we have finished the T-beam design in last lecture, and we will continue today on irregular sections. And after today, and maybe a little bit tomorrow, Monday, we will be finishing all the flexure design. So we'll start talking about shear design on Wednesday as my planning, and I will do a review / office hour next Tuesday. Time to be determined, but roughly between 2 to 3 p.m. I send out invitation once the time has been determined. Okay, now the exam is on the 24th. Next week is a spring recess, I believe, starting from 17th. So I think it's a good time to start preparing for the exam and start reviewing it. Okay, and again, if you have any question about homeworks, please stay behind and we can talk about them. Okay, all right, so today we're going to talk about lecture 10, irregular section. The keyword is analysis. Okay, analysis. And I explain to you why. Okay, now what is the difference between, so first thing, difference between regular section and irregular section, right? So difference between regular and irregular sections. What are the differences? Okay, so when we talk about regular section, let me zoom in a little bit. We talk about regular section, we had in our head, and let me just try to write it correctly, regular sections. And when we think about regular section, what in our head is, first of all, of course, our old friends, rectangular section, right? That's what's popping in my head. At least a rectangular section is regular section, right? Rectangular section is our friend, right? And now afterwards, we talk about the T-beam. We talk about T-beam, so cross this out and T-beam looks just like that, T-shaped beam. We learn how to determine the width of it, the web and everything, right? So this is also considered as regular section, okay? And now if you know how to do T-beam, you will also know how to do I-beam, okay? The difference is that for the I-beam, the lower part usually was not accounted for in terms of tensile loading, okay? But anyway, so this is I section, this is I section, okay? And now that is the regular section in our head, okay? Now in terms of irregular section, okay? And first of all, why do we have irregular section, right? And also that's the second question, but let's take a look at some of the irregular section in my head, okay? Irregular sections include something like this, right? I have a rectangular section, use a different color, rectangular section. And say that for some instance, I have an opening in the middle, right? I have an opening in the middle. Okay, and why do I have opening in the middle? Because maybe sometimes I need to insert a pipe for HVAC, okay, or plumbing or anything like that. Okay, anything like that. Okay, all right, so that's something that we need to know, right? So we need to know have the capacity of this section, right? So with opening in the middle of it. Of course, I forgot to put a reinforcement in there, right? A reinforcement goes somewhere here, for this case, somewhere here, right? And these are rebars, right? Rebars somewhere here. And also we might have a section like this. Okay, so when do we have a section like this? For example, if I have some beams sitting on the shoulder of this beam, right? So I have irregular section just like that, right? Irregular section just like that. And sometimes if I go crazy, architecture point of view, if I want to put in the beam has a special geometry effect, and for example, I want to put a triangular shape, right? So all these are irregular sections. All these are irregular sections. Okay. Now, second question is, and now you see this, right? What would be the main differences, right? Oh, sorry. What would be the main differences, right? Apart from the geometric things, right? So this is 1.1, that this is called geometric, right? Geometries. And second thing is that the stress distribution or stress analysis will be different. Okay, will be different. So why? How different, right? So let's take a look at the irregular section, right? Say I have a regular section like this, okay? And it's nice and straight. I have all these compressive zone and tensile zone built in it. I have all these nice tensile zone, compressive zone built in it. So that means that I have my effective compressive zone, and let's just call it actually the actual compressive zone, right? Let's call it actual compressive. So from the strain diagram, you know that this is lining up with the neutral axis, and now this is so-called C, is the actual compressive zone, right? And the concrete failed, of course, at 0.003 of the compressive strain, right? And I have a reinforcement, say somewhere here, and then that is the epsilon s right here. So the depth of the section is right here, ds. And of course, you know that when we do analysis or design for the concrete beam, we always ensure that Fs is equal to Fy, right? It's the yield strength of the bars. And now if you look at the stress, then use my Whitney stress block. So I have A right here, that's the effective compressive zone. And my total concrete compression is got to be Cc right here, and this half a distance away from the top. And now this magnitude right here, 0.85 F prime C. And I know that my tensile forces right here, right, equal to AS Fy. Okay, so that is the regular section, right? So this is strain diagram. Don't forget the 20%. If you draw this, no matter what in the exam, I will give you 20% promises, okay? So that is the regular section stress strain distribution, right? But what if I cut a hole in it, right? I say, look, I do not want to use this section. I want to cut a hole, cut an opening in it, and I want to put something in it, right? So what happens, right? So what happens is that if I have opening in the compressive zone size CE, and what happens, right? So you think about what happened. Now, first of all, the strain diagram stay the same. Okay, stay the same. Why is that? Because strain is related to curvature, related to bending. So if I have a certain curvature, certain bending of the beam, the strain diagram stay the same. Linear plane remains plane, right? Remains plane. And then the only difference is now is that my compression of the concrete becomes Cc prime, and that equal to 0.85 F prime C AB previously minus 0.85 F prime C A opening. Okay, so that is the first differences. Second difference you have to figure out is that the compressive zone has changed because I dug an opening in the middle of it, right? So the location of the compression force will shift as well. Location of the compression force will shift as well, right? So that will cause several things. So first of all, the total compression of concrete, so concrete compression changes. Okay, concrete compression changes, of course. And second of all, the related moment capacity also changes. All right, so these two parameters actually changes. Okay, so what does it mean? It means that if you have an irregular section and happen to be the irregular part is affecting the compressive zone, right? Affecting the compressive, for example, like this, right? That means that you have to analyze your section differently. Analyze your section differently. So I want to put the word emphasis on the word analysis, right? Analyze or analysis, right? In the irregular section, then you can mark my word that in the exam, I will not ask you to design for it. Okay, I will not ask you to design for it. I basically will ask you to estimate the flexure strength or the moment capacity given a geometry, given the section. Okay, so that is what we're going to do today. Okay, we're going to do analysis, not design. Okay, we're going to do analysis, not design. Okay, all right. So if we are going to do analysis, right? First of all, let's take a look. What kind of analysis we need to do, right? What kind of analysis we need to do? All right. So let's take a look. So example number 1. Okay, and I would say this is primarily analysis, but let's just call it maybe a little bit design, right? Maybe a little bit design, but not much. Okay, and now for this problem, I have a nice rectangular section, and my width of the section is determined to be 16 inches. Okay, geometry is given. Okay, geometry is given, and you may ask me, so Bob, you just said there's just the analysis. Why design? Because I can design for reinforcement, but I'm not going to ask you to design for geometry. Okay, geometry is given. Geometry is given. Okay, so in this nice rectangular section, the 16-inch width, 24-inch of height, I have opening in the middle. I have opening in the middle. All right, and when I say opening in the middle, that this opening has a 4-inch of width, 2-inch of spacing between the top edge to the edge of the concrete and the top, and also 2-inch of height. Okay, and it's located right here in the middle of the section, right here in the middle of the section. Okay, and now given that this is actually 20 inches. All right, so this is the irregular section we're dealing with. So for all we know, the concrete compressive strength of prime C is 4 KSI, curbside concrete, pretty standard. And the yield strength is 60 KSI. Okay, and we're trying to find out Mn. Okay, we're trying to find out Mn. Okay, what is my Mn? All right, and so what to do? What to do? Okay, so first of all, we need to do an equilibrium, right? But before we do everything for this, and let's say solve for this or design or analysis, right? So solve for this. Okay, and please put down this number. For irregular section, you can always assume epsilon t equal to 0.005. Why is that? We want to make sure that the section is tension controlled. We want to make sure that the section is tension controlled, okay? So this is very important. For irregular section, for irregular section, you always want to make sure that the section has a strain of 0.005. So this is for irregular section, okay? For irregular section, you have to make sure that it's tension controlled. So if it is tension controlled, and now I start drawing my strain diagram, right? So the strain diagram looked like this. And of course, this is epsilon Cu at 0.003. And now epsilon S, and let's equal to epsilon T. And I can say that set, this is set one layer of reinforcement, okay? One layer of reinforcement. Again, when I say set, that means it's assumed, okay? This is assumed, all right? So now this is my actual compressive zone C, and this is equal to 0.005. I made assumption for it. So C should equal to epsilon Cu divided by epsilon Cu plus epsilon T, okay? Be careful, T, and multiplied by dt. And of course, in this case, if I assume the one layer, so ds should equal to dt, and that is the depth of the section, okay? So with this, I can start manipulating things, right? Because now I can see that C should equal to epsilon Cu, and that is 0.003 divided by 0.003 plus 0.005 and multiply dt, okay? So if you look at it, this is basically 3/8 of dt, 3/8 of dt. All right, so what is dt? Now, dt should equal to h minus 2.5, right? H minus 2.5. Actually, if I use 2.5, I should say that this is actually 2 layers, right? 2 layers. Is that right? No, this is actually 1 layer, correct? 1 layer, okay? 1 layer, 2.5, okay? So that means I have a 24-inch minus 2.5 inch, so that is 21.5 inch of a depth for dt, okay? Now, given that F prime C is 4 KSI concrete, so A naturally should equal to beta 1C, and that is equal to 0.85 multiplied by 3/8 of dt, so 21.5 inch right here. Okay, 21.5 inch right here. Now, save the trouble, I calculate this out. A equal to 6.85 inch. That is the effective compressive zone size. And now, when I see this number, okay, and be careful, folks. You might think it's Thursday afternoon, Bob's tired, we're all tired. Let's just repeat the things and don't worry about the question. No, right? I'm a very annoying professor. I will ask you questions, right? So be careful, guys, okay? You see that this is the so-called effective compressive zone, right? Mind you that this is the A right here, right? So this is A, and A equal to 6.85, okay? So when I see this, right? First thing I had in my mind is that to see if my opening is in the compressive zone or not, right? So which number should I compare it to? I'll give you a hint. A should be bigger than what? What number I should compare it to? Now let's start pick my victim right here. I had A, I had a B, I had a C. I didn't have, well, I had a D before. Let's try Danny Wilson. Hello, Danny.
Hi.
Hey, how are you doing?
I'm doing good.
Good, Ms. Wilson. So can you help me out here? So I want to ensure that my opening is within my compressive zone, right? So I just estimated I have my effective compressive zone A size equal to 6.85 inch. Now, what number should I compare that with to ensure that my opening is within the compressive zone?
Would you compare it to the height of the opening?
Right, so that is absolutely correct, Danny. Very much, thank you. And that is 4 inches. Okay, so this is very important. Why? You say, why, Bob? Why this is important? Everything seems important. Yes, of course, this is important. Because remember, if I have this kind of thing, and thank you, Danny, again. And I have my opening, so now I can use this fellow right here, subtract this fellow right here, isn't it? Right? So I can do a subtraction, right? Superposition method, I can do the calculation. So if not, I cannot do this way, right? I cannot do this way. So let me just put out here. So example number one, this is when opening covers the, when compressive zone, effective compressive zone cover the opening. Okay, effective compressive zone covers opening. Oh, sorry, covers opening, right? So that is important. So which means in the case of A bigger than opening, right? So whatever gap you have here, right? So let's just cut H opening. Okay, right here. Okay, so when that happens, I'm happy, right? I'm happy. I say, okay, look, this means A is bigger than H open, and okay, scenario number one, right? Scenario number one. And for that, I say now I can establish my equilibrium. So equilibrium reads like this. Equilibrium reads like this. That is C, the total compression, CC equal to 0.85 F prime C bracket inside AB minus the area of opening. And I just call it a hole right here. And that is so-called AC. Okay, see, Bobby confusing me. Why introduce another parameter? Because this is so-called actual or the compressive zone, compressive area, right? Compressive area. Compressive area. Okay, so with that, I say that this is total compression now because I can do the subtraction because it's only because I can do this, right? I can do the subtraction, A bigger than the height of the opening, so that equal to ASFY and equal to the total tension force. So with that, I say, look, I now can determine my area of steel that should equal to 0.85 F prime C and multiply AC divided by Fy. Okay, so AS should equal to 0.85, bring the number in. For KSI of a concrete, area of the compressive zone is A and B, so 16 multiplied by 24 minus, what is the area of opening? Let's take a look, right? So 4 this way, 2 this way, so 2 by 4, 8 inch square, so 8 inch square. And let me just write it out in case you're confused. So 2 inch by 4 inch of opening, so that is the total compression I have. And divided by a yield strength of the bar, 60 KSI, I have AS equal to a 5.76 inch squared. 5.76 inch squared. 5.76 inch squared. Okay, so that is how much reinforcement I need to have for the irregular section, All right, normally at this point, you say that, look, this is required. So this is required steel, and I need to select the bars, right? So if I pick number 9 bars, I'm going to select 6 number 9 bars and go back and treat it as analysis and doing it all over again, right? But let's just say miraculously, I have a way, I say, I will provide exactly this much reinforcement, just to make our life easier, right? 5.76 inch squared. Miraculously, okay, miraculously, just say that somehow, I find a way to provide this much. Okay, so now the game is simple because if I can provide this much, right? If I can provide this much, all I have to do is to do a subtraction. So from the opening, and this is the actual compressive zone, AC right here, right? This is AC, right? And so that equal to the compressive zone of A. Okay, subtract, right? Subtract the same section, but with a tiny compressive zone of opening. Okay, so tiny compressive zone of opening. Okay, so if I can do that, then I can start writing my equation. So Mn should equal to the compression from the total area of the compressive, right? Compressive area, right? Plus this, minus this, right? Multiply the lever arm, which is JD. Okay, but I can now do the subtraction, so which is 0.85 F prime C A B, this fellow right here, multiply lever arm ds minus half A. Okay, minus minus, okay, 0.85 F prime C and A whole, right? Opening, area of opening, right? And then multiply ds minus, what is the center? So the distance between the reinforcement ds right here, right? Reinforcement is that ds, and this is so-called JD2, and let's call it JD1. So JD1 naturally equal to this distance right here, JD2 equal to this distance, and JD2 equal to ds, which is the depth, minus this distance right here, right? So this is 2 inch of a gap given, and this is 2 inch from the top of the opening to the center of the opening. So 4 inches. This is ds minus 2 and minus, oh, sorry, now 2 minus 1 again, okay? Minus 1, okay? Because the height of the opening is 1 inch, okay? Let's take a look, right? So there you go. The height of opening is 2 inches, so the middle of it is 1 inch, okay? Oops. So that is the JD2, that is the lever arm, okay? So with that, I can easily compute, bring the number in, mn, then equal to 0.85, carry the number here, multiply f prime c 4 ksi, multiply a, which is, what is a? 6.85 inch. And what is the b here? B is 16 inches, right? And multiply inside the bracket ds, and ds equal to dt, one row reinforcement, assume that between 1.5 inch minus 6.85 inch divided by 2, and minus, I'm just going to drag the whole number down here, 0.85 for ksi, and then area of the opening. What is area opening? So area opening a 2 by 4, so 8 inches, so 2 inch by 4 inch. That's the area of opening. And then multiply by the distance, right? 21.5 inch right here, minus 3 inch, and voila, there you have it. Okay, now after everything is done, this is basically Kip's inch, right? And need to divide by a 12 inch per foot of a unit conversion into Kip foot. So mn should equal to, end of the day, 519 Kip foot. Okay, so that is how you compute the moment capacity. Okay, now while we're here, right? You know that this is not the destiny. This is not the champion, right? This is semi-champion finals, right? It's not the final, right? So to get a final, to get a championship, you need phi mn, right? Remember phi mn, okay? Now we have mn, but we don't have phi, so I'm gonna pick my next victim here. So let's see who's here. I have D now, and E, I have one guy, so I'm just gonna skip him and see. Jonathan, are you there?
I'm here.
Hey, how are you doing, man?
Pretty good.
Oh yeah, good to hear that. So what is my stress reduction factor in this case, sir?
Would it be 0.005?
Well, that's the strain, right? You're talking about epsilon t equal to 0.005. Great. But what would my stress reduction factor to be? Let me try to help you here. So that is my stress reduction factor, right? So when epsilon t is smaller than 0.002, what would be my phi?
0.65.
There you go. And if I have 0.005 or beyond that, what would my phi be?
0.9.
0.9. There you go. So what would be the phi in this case?
That would be 0.9.
0.9, exactly. Thank you so much. So that is my phi. Okay. So with that, we can compute the final capacity of this thing. Okay. And please help me out here, but you can finish the rest, right? So you can see that in doing analysis / design of an irregular section, we use this assumption here, epsilon t equal to 0.5, tension controlled, and then come up with a reinforcement area. Of course, you might slide in 6 inches squared, but when you do have 6 inches squared, you might sacrifice your strain a little bit, right? So oftentimes we provide as accurate as possible and then come up with the moment capacity. Okay, because oftentimes when we were forced to do this irregular section, we are in the case that the space is confined, there's not much of space, or the design is finalized. So we have to go with the design. So most of the cases, we're not really designing it. We're basically doing analysis for it. Okay. All right. So this is the irregular section with the opening inside the compressive zone. Okay. I'm just going to pause here. Any questions so far on this? Any questions, guys? Anything strange? Don't understand? Fall asleep? Any questions for me, sir? Ladies? Anything? Ladies, sir? Anything? No? All right. Well, assume you all understand and we're on the same page. Let's move on, right? Move on. So that is first example, right? So when opening in the compressive zone, when opening is in the compressive zone, how about when the opening is not fully into the compressive zone? Okay, so I am going to show you an extremely carefully designed case where that I have irregular section with opening that is outside the compressive zone, outside the compressive zone. When I say outside, they're not really fully outside, okay? Because if they're fully outside, it doesn't matter anymore. Remember, if they're in a tensile zone, it doesn't matter anymore, right? But we're talking about I have a nice rectangular section, but with this opening at the top. Imagine this is probably some aqueduct I'm trying to build here and have opening right underneath it, like so. Okay, and with this section, I say that there's a 4-inch of the top here and 4-inch in the middle, 4-inch on the right-hand side. And I also know that this protrusion is 4 inches and opening here is 2-inch spaced away from the top edge and another 4-inch in the width of it. And then the rest of it is 8-inch. Okay, and I put a bar right here. That is my AS. And then I end up with a 2-inch concrete cover on the lean side, okay? Pretty much on the lean side, but I have a width of it, which is 1 foot. And of course, the total height comes up to be 20 inches. All right, so that is a very weird irregular section with opening that may not necessarily fall inside or maybe falling outside the compressor. We'll talk about that, all right? But F prime C equal to 4 KSI, same curbside concrete, grade 60. That means Fy is 60 KSI. And then I have an area of steel. Let's just say I provide that already, save you the trouble for analyze or design for it, right? So it's 4 number 9 bars and 4-inch squared of steel, okay? 4 number 9 bars. And I'm asking you guys to find out VMN. Okay, so that's the second example. All right, now you look at this thing, right? You say that, look, all I need to do is to find out whether my compressor zone covered the opening or not first. First, I need to find out whether my compressor zone covers the opening or not, right? To determine that, we need to solve first, right? How to solve it? And we know the tension force has been fixed. Now, I'm not assuming 0.005 anymore because I know the steel, I know the area of steel, okay? I know the steel, so I can start with the tension force that is 4-inch squared of steel multiplied by 60 KSI of U strands of steel, gave me a 240 kips of total tension force. All right, and from there, I can do equilibrium, that is tension equal to compression. So ASFY equal to 0.85 F prime C. Now, normally for rectangular section, it follows by an A and B, but here, since I don't know what is my compressive zone, so I'm just going to put AC here, and I say, this is the things I need to determine. Okay, this is the things I need to determine. So from there, you say AC now equal to ASFY divided by a 0.85 F prime C, which is 4-inch squared, and multiplied by Fy. I have that number calculated out already, 240 kips. Okay, and divided by 0.85 at prime C is 4 KSI. So I got this number to be a C equal to a 70.6 inch squared. 70.6 inch squared. All right. So when you look at the thing, right, 70.6 inches squared, where is that, right? Where is that? Does it cover the opening or not? We don't know, isn't it? We don't know. All right. So if we don't know, let's make some assumptions, right? Let's make some assumptions. So I say that, look, how about I just cover or I just copy this section right here because I'm going to use it again. And I say, look, I am going to do some analysis, right? Some analysis. And let me just take out this thing here, take out this thing here. And I say, look, I can start doing analysis. I say, if I call this tiny two little wings, right? I call this shaded and I call it 1 here, zone 1 here. All right. If I call it zone 1 here, then I can cut another strip right here underneath it and call it zone 2, can I? All right. And now if my AC is bigger than A1 plus A2, then yes, I'm in trouble, because now that means that my opening is not, right? My opening is not, but will affect my compressive zone, right? And let's just say that also I can do another thing. If I say this is a little bit on the side, and let's call it zone 3 now. And if I say that AC is smaller than A1 plus A2 plus A3, then it means that my compressive zone does not cover, compressive zone does not cover the opening. Okay, simple geometry, right? So if AC is smaller than A1 plus A2 and plus A3, that means that it does not cover the opening. Okay, to make our job easier, right? I let you know now for now already that this should be the case that it does not cover the opening, but how much? How much, right? So second step, we need to, third step, we need to find the centroid of AC, or more specific, the size, right? The compressive zone size. So let me just get it clear here, the compressive zone size. Okay, ooh, yeah, there you go. So how to find that? How to find that? So let's do some analysis. So A1 area in zone 1 should equal to 4-inch, this fellow right here, multiply 4-inch, this fellow right here, multiply 2, because I have 2 extrusions, right? 2 pop-out things, right? And then that equal to a 32-inch squared. All right, now A2, easy, right? Just this red strip here. So 12-inch in the width direction, and the height is 2-inch. So multiply 2, I have 24-inch square of strip 2. Now A3, okay, supposedly would equal to 4-inch on the side, and this is another 4. So it's just like A1, right? So equal to A1, and that is 32-inch squared. So you do the calculation, 32 multiplied by 2, that is 64 plus 24, that is 88. So A1 plus A2 plus A3 definitely bigger than, well, let me just put the number here, equal to 32 multiplied by 2 plus 24, so 88-inch squared, and definitely bigger than AC, and that is 70.6-inch squared. So yes, it does not cover it. Does not cover it. Okay. All right. So if it doesn't cover it, right, I start asking myself a question. If it doesn't cover it, I'm going to use the same drawing again. Okay. You would see that I'm going to use the drawing again in this problem. Okay. Just do some detailed analysis. I know this is boring, but bear with me. We really need to find out the bottom of it. Okay. Find the bottom out. Okay. So now if I'm doing this, I need to find out if this does not cover it, right? So let's assume this is how much the compressive zone ends. Okay, the blue line is where the compressive zone size ends. So let's call it A right here. Okay, now I need to find out that. I need to find out that, right? So how about I use my zone 1 and zone 2, and I call this 3 prime, zone 3 prime, right? So let me use a purple color to make it a little bit different. So it's 3 prime. How about that? And to further differentiate, let me just call this tiny height. Zoom in, zoom in, zoom in, tiny height, right? Let me call this H3 prime. H3 prime. All right. Now my job is to find out this H3 prime. And how to find that? Basically, AC should equal to A1 plus A2 plus A3 prime. And A1, we know that, right? So AC is 70.6 inch squared. A1 equal to a 32 inch squared. A2 is 24 inch squared, that right? Yeah, 24 inch squared. A3 equal to what? A3 equal to 12 minus the opening. The opening is what? Let me take a look. The opening is 4 inch, right? So this is basically 12 minus 4 multiplied by H3 prime. Okay, so now I can do the calculation. So basically H3 prime after my calculation, save you the time again, 1.825 inch. 1.825 inch. If that is the height of this zone, the purple zone 3 prime, so the A, which is my effective compressive zone size, should equal to 4 inch plus another 2 plus H3 prime. So it's 4 plus 2 plus H3 prime. And now you end up with 7.825 inch. Okay, 7.825 inch. Okay, and that is my compressive zone size A. That is my compressive zone size A. So now, okay, after everything said and done, I have my compressive zone mapped out. I have my compressive zone mapped out. Okay, but I am not so happy yet because the whole effort, everything I have been doing so far is actually to find the centroid of this compressive zone, the geometric centroid of this compressive zone. How do I find that? So let me copy this image again. Yes, very tedious. Okay, that's why today's going to be a little bit boring. And unfortunately, in the exam, you'll see a problem like this and you knock on your head and you will regret if you're not paying attention right now. Okay, you will regret if you're not paying attention right now because the exam will have a problem identical like this. Okay, so now knowing that after everything said and done, I will end up an effective compressive zone somewhere right here. And the total area of compression is AC equal to 7.6 inch and have a zone A equal to, just calculate out, 7.825. And I need to find the centroid of this blue shaded area. Centroid of this blue shaded area. Okay, how do I do that? How do I do that? Well, you got me, right? It's pretty complicated. It's pretty complicated. Okay, but we can always go back to our old friend that to define a distance, that is the distance between this centroid and to the top edge of the section, okay? Top edge of the section, and let me just call it y bar. So the job is to find y bar. Okay, now when I see y bar, I memorize so many times, I know that the equation to find out y bar is sigma ai yi divided by sigma ai, and ai yi is called so-called static moment, that is area multiplied by distance of each pieces divided by the total area, right? So that means y bar equal to a1, remember zone 1 and y1 plus a2 y2 plus a3 prime y3 prime divided by AC. Okay, why AC, Bob? AC because it equal to this plus that plus this. Remember? Okay, so I use that equation. I'm going to use this equation. I say, look, y bar will be A1. What is A1? I just calculated out 32 inch squared from previous calculation. And the distance Y1, that is from the center of the little extrusion, right? So it's right here to the top of the section, right? So that is basically 4 divided by 2, 2 inches. So 2 inches right here. Okay, now plus A2, what is A2? A2 is 24 inch square, right? 24 inch square. And the distance is this distance right here. So I'm just in a different color, okay? This distance 4 inch right here plus half of this right strip right here, right? So this 4 plus 2 divided by 2. So that is 1 inch, right? And that is the Y2. Okay. And last but not least, me switch the color back again to black. So this is A3 prime. What is A3 prime anyway? That is 14.6 inch square. I calculated out from previous calculation, and Y3 bar is what? Y3 bar is 4 plus 2 and plus 1.825 inch divided by 2. Don't forget divided by 2, okay? Divided by 2. So now that, ladies and gentlemen, is my Y bar on the top and divided by 670.6 inch square of total compressive zone. Okay. All right. Yes, it's pretty hardcore, right? So after you do everything Y bar and save you the trouble, you can do the calculation, check me later, but you end up with a 4.94 inch. That means this distance right here is 4.94. Okay, 4.94. All right, and if that is 4.94, what does it mean? It means that if I were to find the strain diagram, and now I don't even want to take a look at it because I know it doesn't matter. I have this one equal to 0.033 anyway, and I want to take a look at this, my stress distribution diagram, and now Y bar, ladies and gentlemen, is the distance between the total compression to the top surface. And then if I say this is where the steel is at, and then this is ASFY, now the lever arm, JD should equal to DS. By the way, this is DS, depth, right? So DS minus Y bar. That's what I'm after. That's what I'm after, okay? To make it more important, this fellow is only for irregular section. So after myself going through so much troubles, all I'm trying to find out is the distance between the compression and the tension. All right. Now, after all these trouble, boom, 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 4 drawings afterwards, now I am ready to do what? To check the strain in the steel. Check epsilon S and epsilon T. Okay, so A equal to 7.825 inch. C, this is steel, okay? C is the what? Is the actual compressive zone, right? So equal to A divided by beta 1. So 7.825 inch divided by beta 1 for the 4KSI concrete 0.85 equal to 9.21 inch. Okay, so that is my C. So epsilon S, and assuming one layer of bar, right? Assuming one layer of reinforcement, okay? Always. And assume that make your life easier, right? So equal to ds minus c over c multiply epsilon cu. So ds in this case 18 inches, c is 9.21 inches divided by 9.21 inches and multiply 0.003. So you end up a strain of 0.00286. Okay, I am going to ask you guys a question. So wake up. Okay, be careful. Okay, now let me give you an explanation, right? So we went through all the troubles. Just find out the strain in the bars, and this doesn't matter the total or the bottom layer, but the strain in the bars is 0.00286. And then let me see who's on my list now. I got this one, Sean. Okay, Sean, are you there? Sean.
Yeah, I'm here.
How are you doing, sir?
Pretty well. How are you?
Not too bad, not too bad. It's great Thursday, right? So epsilon T and equal to epsilon S was 0.0286. Am I happy about it? Or should I be happy about it?
Well, it's not in the tension controlled area. It's in the transition zone. So,
exactly. So this is in the transition zone, right? So what does it imply?
we gotta calculate for a phi value.
Right, phi or phi, right? Strength reduction factor, right? Great, thank you so much, Sean. So this means, okay, this means it's in the transition zone. So I am lucky that is larger than 0.0027. So the steel at least yielded. Very happy, okay? Why am I happy that at least the steel yielded? Because I used the yield strength for the bars to calculate tension. right? But I'm not happy because it is smaller than 0.5, so not tension controlled. So make my job a little bit complicated. I have to calculate my phi or phi, right? Stress reduction factor. So there you go, find out phi. And of course, Mn. All right, so now I know phi, use that equation, equal to 0.65 plus epsilon s or epsilon t, in this case, minus 0.02 divided by 0.03 and multiplied by 0.25, or we can use the other equation, that's fine. So phi should equal to 0.72. All right, save you the trouble. But now my Mn, which is the bending moment, is not so bad. So Mn equal to T, tension force, multiplied, don't forget ds minus y bar. ds minus y bar only for irregular section. Let me label this out. Only for irregular section. And if you really want to know, that does not cover the opening. My write up. Sorry, does not cover the opening. Okay, so only for this case I can use this equation. So ASFY 240 kips calculated previously, and multiply ds is 18 inch. I know that already. 4.94 inch of y bar. I know that already. Convert back to 12 inch per foot to get my kip foot. So eventually this becomes 261.2 kip foot. Okay, so phi Mn, which is my 0.72 multiplied by 261.2, so end up 188.06 kip foot. That is the capacity for this irregular section. Okay. All right, so this is how much I would like you to know about irregular sections. All right, and later today or tomorrow, I will post the homework for the irregular section and T-beam design, okay? For irregular section and T-beam design. And then with this, we are done with all the content. Let me repeat, we're done with all the content that to be covered by exam number 1. Okay, all right. So with this, I think today's section is over. Please stay behind if you have any questions or regarding the homework, regarding class, anything. And other than that, I will see you on Monday. Okay, thank you so much.